Have you ever just looked at a beam of sunlight? I mean, it looks totally white, right? But then, all of a sudden, it can just burst into this brilliant rainbow. Well, today, we're going to pull back the curtain on one of the most beautiful tricks in all of physics, the colorful secret that's hiding inside what we call white light.
Okay, let's just dive right into the big question. This is the whole mystery we're here to solve today. I mean, it seems completely impossible, doesn't it? That this pure, basically colorless light is really just a mask for a full-blown spectrum of color. So, where do we even begin to look for clues? Well, it turns out the very first one is hiding in a simple little piece of glass. Our whole investigation really starts right here, with a prism. When you shine a beam of light through one of these, something pretty spectacular happens. And no, it's not magic, but it is a fundamental property of light that, you guessed it, has a very specific name. So the official term for this whole phenomenon is dispersion. It's literally the process of white light splitting apart into all of its individual colors. You can think of the prism as kind of like the key that unlocks that hidden rainbow, making it totally visible to our eyes. All right, so if the prism is just the tool, right, then the real secret has to be hiding inside the light itself. So let's put our prime suspect, this plain old white light, under the microscope and see what's really going on. This, right here, is the key question. We see it as just one thing, light. But what if it isn't one thing at all? What if it's actually a team, a composite of other things all working together? Well, the answer lies in one simple number: 7. You see, white light isn't a single color at all. It's actually a perfect mixture of 7 distinct colors, all traveling together so seamlessly that our eyes just get tricked into seeing them as one. And here they are. This is the hidden team: violet, indigo, blue, green, yellow, orange, and red. And there's a really handy acronym to help you remember the order: VIBGYOR. Just sound it out. These 7 colors, they're the fundamental building blocks of all the white light you see. So now we know what's inside white light, but we still need to figure out why it splits apart when it hits a prism. And honestly, the best way to think about it is like a race. The moment these colors enter a new medium, like glass, the race is on. So why do they split? Well, it really just comes down to this. Not all colors are created equal. Each one has this unique property called a wavelength. And that difference in wavelength means each color travels at a slightly different speed once it's inside the prism. And that change in speed, it forces each one to bend at its own unique angle. Let's look at the two extremes of this race, okay? On one side, you have red light. It's got this long, stretched-out wavelength, which makes it the speedster of the group. It zips through the prism the fastest, and because of that, it bends the least. But on the other end, you've got violet, with its short, compact wavelength. It's the slowest of the bunch, and it gets bent the most. So let's trace the journey step by step. First, that single beam of white light hits the prism. Instantly, all the colors slow down and they start to bend. That's called refraction. But because each color bends by a different amount, they start to separate from each other. By the time they come out the other side, they fanned out into this beautiful, perfectly ordered spectrum. And this right here is the result of that race. The final lineup is always the same. Red, which bent the least, is at one end of the spectrum, while violet, which bent the absolute most, ends up at the other. And all the other colors, they file in perfectly right in between. Now, this isn't just some cool lab experiment. This principle is at work all around us, all the time, creating some of the most stunning sights in nature, and believe it or not, enabling some pretty powerful technology. And yep, here's the most famous example of all. A rainbow is just dispersion happening on a massive, massive scale. After a storm, the air is filled with millions of tiny little water droplets, and each and every one of those droplets acts like a tiny little prism, taking in sunlight and splitting it into that beautiful, familiar arc of color we all know. But this principle is so much more than just beautiful. It's incredibly powerful. Scientists use dispersion in devices called spectrometers to analyze the light coming from distant stars. They can literally figure out what stars are made of from millions of miles away. It's also used to identify chemicals right here on Earth and to create that dazzling sparkle you see in diamonds and other cool optical effects. So let's kind of wrap this all up by making sure we've locked in the core principle. It's really important to distinguish dispersion from a related concept you've probably heard of: refraction. They're related, but they're not the same thing. This chart really breaks it down nicely. Refraction is just the bending of light. Simple as that.
Dispersion, that's the splitting of light. But here's the crucial thing to remember. Dispersion only happens because of refraction. You see, without the bend, you can't get the split. One causes the other.
And look, if you walk away with just one thing, let it be this core idea. Dispersion is the splitting of white light into its 7 colors as it passes through something like a prism. And it all happens because each color's unique wavelength causes it to bend at a slightly different angle. That, right there, is the secret behind every rainbow. So, the next time you see a rainbow in the sky, or maybe a flash of color from the beveled edge of a mirror or a diamond, you'll know exactly what's happening. And it kind of leaves us with a fascinating question to think about. Where else in your world can you spot these tiny, hidden rainbows happening all around you?